Have you ever seen something that just seems to defy gravity? Well, today we're diving into a design principle that does exactly that. It's the kind of hidden architecture that shapes everything from these delicate, beautiful sculptures to absolutely massive bridges, and believe it or not, even the very cells inside your body. So let's see how it works. All right, to get started, I've got a little puzzle for you. The structure we're about to see really challenges our basic ideas about how things are supposed to be built. See if you can wrap your head around what's going on here. Okay, look closely. See those solid green bars? Those are the struts. Now here's the weird part. They aren't touching each other at all. They look like they're just floating in midair, held there only by that web of thin red cables. So, what's going on? That's the big question, right? How is that even possible? How can a structure be strong and stable when its solid parts, the parts that are supposed to be holding everything up, are completely separate from one another? This is the whole mystery behind what's called floating compression.
Well, the answer lies in this really brilliant and surprisingly elegant concept. Let's unpack the rules that make these seemingly impossible structures not just possible, but incredibly strong.
The name for this is tensegrity. It's a word that the architect Buckminster Fuller came up with back in the 1960s, and it's literally a mashup of tensional and integrity. The core idea is actually pretty simple. You have isolated parts that are being squeezed, that's the compression, and they're being held in a perfect balanced state by a continuous web of things being pulled, that's the tension. Now this is a total 180 from how we usually build things. I mean, think about a simple brick wall, right? The bricks are stacked and they push their weight directly down onto the bricks below them. But in a tensegrity structure, those compression parts, the bars, they float. They never touch. Instead, any force that hits the structure gets distributed throughout that entire web of tension cables.
You know, a pretty good way to get your head around this is to look at the Skylon Tower from way back in 1951. See how that central pillar isn't really resting on anything? Its exact position in space is locked in, held firm, by the tension in all those cables pulling on it from every direction. Now imagine that every single strut in a tensegrity structure is held in place just like this.
So once people figured out this pretty mind-bending idea, what did they do with it? Well, it turns out this principle has allowed us to build some truly incredible things, from beautiful art to massive feats of architecture. And what's really cool is that this whole idea didn't even come from engineers. It actually started in the art world. Back in 1921, an artist named Carlos Johanssons was playing with some of the early concepts. Then, in 1948, Kenneth Snelson, who was actually a student of Buckminster Fuller, created this groundbreaking XP sculpture. And it was Fuller who, years later, gave it the catchy name and really pushed the idea out into the world. And man, has the idea scaled up. On the left, you've got one of Kenneth Snelson's elegant little sculptures from 1948. And on the right, that's the Kurralupa Bridge in Brisbane, Australia, the biggest tensegrity bridge in the entire world. It's the exact same principle, just taken to a completely epic engineering extreme.
And it's not just bridges. Tensegrity is absolutely perfect for spanning huge open spaces. The roofs of famous venues like the Spodek Arena in Poland, the Seoul Olympic Gymnastics Arena, and even the Georgia Dome. They're all held up by these incredibly lightweight yet amazingly strong structures.
But for all of these massive, man-made structures, the most profound, the most common application of tensegrity isn't out there in the world. Nope, it's much, much closer to home.
Yeah, it turns out nature figured this principle out a long time before we did. The exact same rules that hold up bridges and stadiums are also the fundamental blueprint for life itself, and this is a field called biotensegrity.
Dr. Stephen Levin came up with the term, and it's all about applying these rules directly to biology. Just think about your own body for a second. Your bones, they aren't stacked up like a pile of bricks. They actually act like those isolated compression struts we saw earlier, kind of floating inside this continuous, tension-filled network of your muscles, your tendons, and all your connective tissues.
It's really amazing when you think about it. Your bones are the struts, and your muscles and tissues are the cables. This whole system gives you incredible strength, but also flexibility and resilience because it distributes forces across your entire body. And this insight is totally changing fields like physical therapy. But it goes even deeper. The very skeleton giving shape to each and every one of your cells, that's a tensegrity structure too. Okay, so if this principle is inside us and it's in our biggest buildings, where is it headed next? Well, engineers are now borrowing this ancient idea from biology to design the next generation of robots.
So say hello to the Superball bot. This is a prototype rover that NASA is developing. I know, it looks more like a sculpture than a robot, but its design is actually perfect for the crazy challenges of exploring other planets.
So why would you build a space rover like this? Well, there are some huge advantages. First, it's incredibly lightweight, and when you're launching things into space, every gram counts. Second, it's super resilient. You could literally drop this thing onto a planet's surface, and it would absorb the impact without needing any heavy, complicated airbags. And get this, it could even move around by just changing the length of its cables, allowing it to basically roll and squish its way across rough terrain.
And this quote from Dr. Donald Ingber, who's a pioneer in biotensegrity, really gets to the heart of why this all works so well. Tension forces naturally want to travel along the shortest path between 2 points, right? Well, tensegrity structures are perfectly arranged to take advantage of that basic fact of physics. It's maximum efficiency built right into the geometry.
Tensegrity shows us that real strength doesn't always come from just being solid and rigid. Sometimes it comes from a balanced, flexible network. It's a principle that scales from the tiniest parts of our cells to the giant things we build, and even in the technology of our future. It really makes you wonder, doesn't it? What other hidden forces like this are shaping our world, just waiting for us to see them?